write down the answers here. Well, you know what? We'll do it out loud, and then I'll write the answers. So BEF2. Who thinks they know that? Todd.
Beryllium fluoride.
Beryllium fluoride. Very good. Beryllium fluoride.
Is it
Good
two
job.
words or one word?
It's 2 words.
Okay. That's
Beryllium space fluoride. Yeah. So
it's just like
yeah, it looks like the same word, but I don't worry about details like that. You're not going to lose points like on our regions. If you got the really, we're looking for that I, not the ion, right?
Mm-hmm.
Fluorine, ione. So, questions on that one? BEF2. Okay, next one. Who's got it? CUS, and there's got to be a Roman numeral. You retracted your.
Copper 2 sulfide.
Very good. You're happy with that one. Good job, Shane. Copper 2 sulfide. I, because sulfur becomes sulfide in a compound. Why copper 2? Here's why. Well, if there's only one Cu in one S, now that means their charges must add up to 0. So I don't need a subscript. Well, copper can only be +1 or +2. We just went over that. What about sulfur? Everyone finds sulfur on the periodic table. There's 3 options, right? -2, +4, and +6, right? For now, because I'll be honest with you, for now, we're going to use that top charge. I'll throw out some random percent. 90% of the time, it's always -2. But 4 and 6, the +4, +6, shows up sometimes. We'll talk more about that tomorrow or Friday. But basically, if you always use the top charge for all the nonmetals, like look at nitrogen, it has like, what, 7 of them? Something like that. But it's -3 pretty much all the time. So use that top charge, and your life's going to be easier with this. All right? So, why am I saying that? S is -2. So, after all that, S is -2, that's the top charge. Well, if S is -2, and there's only one S, and copper, there's only one copper, then this has to be +2. Has to be. Because these two add up to 0. Therefore, since there's a 2 there, it's copper 2. I already wrote it. Sorry. Copper 2 sulfide. Copper 2 sulfide. Questions on the first 2 there? All right. AlCl3. Who wants this one? AlCl3. Go ahead, Quinn.
Aluminum chloride.
Aluminum chloride. Yep. Aluminum chloride. And beryllium fluoride and aluminum chloride, these two, they don't need Roman numerals because they only have one charge in the box. Be must be +2. Al must be +3. So you don't need Roman numerals. You only need them when there's 2 charges in the box for the metals. Non-metals, we use the top one. Questions on this one? Okay. Sodium oxide. Go ahead, Jake. Good. Na2O. Sodium oxide. Very good. Here's how he knows this. Na is +1. Go over to the right. O is -2. Does that add up to 0? No. So I need 2 of these to cancel out one of those to 0. So Na2O. Some students need to do it this way. They need to write it out. Say, okay, I know Na is +1. I know O is -2. I need another Na +1. So if you need to do that, then do it. Do whatever you need to do, as long as you can come up with a formula. You don't have to do it all in your head.
No.
You don't have to do it.
Could it be like other ways also?
Well,
If we could do like, say, do Na4 and then O2.
Oh, I see what you're saying. You could. Good point. But we're going for the lowest ratio.
Okay.
So if you can reduce the subscripts, then do it. So you're right. 4 and 2 would also add up to 0, but they reduced to a 2 and 1. Good question. All right, next. Iron 3 bromide. Becky, what do you think?
FeBr2.
FeBr in here.
2.
Close. Say loud.
3.
3, yeah. FeBr3 is the answer, and here's why if you were confused. Iron 3, so the first part of the name means this. Iron 3 is Fe +3. The Roman numeral tells me the charge. So you actually don't even need to look at your periodic table for that. if it gives you the Roman numeral, you don't need to look in the box. That's telling you it's +3. But it doesn't hurt. If you look inside the box for FE, it's +2 and +3 in the top right corner. It's going to be one of those two. So this means we're using this one, +3. All right. What about BR? Fred, what's the charge on BR? Over on the right, 35. -1. So we need 3 of these to cancel out one of those. So it's FeBr3. Questions? You wait. Good. Calcium chloride. All right. Let's see. I'm going to call on somebody here. Corey. Calcium chloride. I want to write more. 2. Very good. CaCl2. Here's why. Calcium. Top right corner. What's the charge? Anybody, just say. +2. What's the top charge for Cl? -1. So I need 2 of them. So CaCl2. Part of the cool thing here you're learning, if it's cool to me, I don't know if it's cool to you, we'll find out after I say it. So if you go to the store, I don't care what you're buying, some chemical or some food, hopefully the food isn't chemicals, you can look at the ingredients and you can actually start to kind of figure out what is in what you're eating. Like you can read like calcium carbonate. What is that? You can start figuring it out. It's kind of cool. Baking soda, you'll learn the formula for that. Vinegar, you learn the formula. So you kind of, I do this, I know I'm probably crazy, right? If I pick up something, I'm like, wonder what's in it. And I'll look at it. And most of the things I try and eat have ingredients I can spell and understand, and very few ingredients, but some stuff, like anyone eat boxed rice, like with the packets, a lot of people, right? My wife buys that and makes it, my in-laws love to eat that. There's more ingredients in that, so if you're reading through it, especially preservatives, they have names like this, which it's a little scary, you know, like what's in there. But now, once you learn this, you can at least kind of have an idea of the chemicals and elements that are in what you're eating. Is that kind of cool?
Scary.
A little tiny.
I'd rather not.
You'd rather not know?
Yeah, I'd rather not.
Now the thing is, though, the word chemical's loaded, so.
Yeah, what technically is the chemical?
Right, so like water could be considered a chemical, you know, so it's like all chemicals aren't bad. Vinegar, it's not really bad for you, there's actually some health benefits to it. Baking soda, you can eat that, it's a chemical, you can eat it. So it's hard to define. I wouldn't, I guess, I mean, I have definitions of a chemical, but it kind of changes depending on where you are. So if you're using something in here for a chemical reaction versus in your kitchen, it's a little different, but they're both considered chemicals. But anyways, that's kind of cool. I think it's cool. Moving on. Take out your notes if they're not open already. And I'm going to write 2 more practice problems on the board using table E. All right, so write these down. Here we go. Let's go with iron 2 sulfate. And so you're going to give me the formula for that. But in your notes, write the name as well, so you have both. And I'm going to give you a formula. You give me the name. Oh, what did I use this morning? It was a good one. Calcium hydroxide. I'm trying to trick you there. We'll see who's paying attention. Oh wait, I did that backwards. I wanted to give you the formula. That's okay. Just give me the 2 formulas for those. Your homework will practice the other way. is Mr. McCoy. Is that gonna work, or did I give the wrong stuff? Okay, all right. I wasn't, because I just read the email and I gave you methyl blue, not methylene blue, and maybe it's the same. Okay. Yep. Got it. All right. Was that enough time? Hopefully. Who wants iron 2 sulfate? Well. FeSO4, very good. Good job. And again, I really want you guys doing that. FeSO4 is correct. Here's why. Fe, iron 2, means it's plus 2. On table E, SO4 is minus 2. Now, after class this morning, someone came up to me and said, why is the 4 inside the parentheses? And I said, because SO4 is the ion. So it isn't an S and an O, and then 4 of those. That's not what it is. It's SO4 together. So you have 1 S and 4 O's bonded to it. I know this is like confusing, like what is that? It's just a group of atoms that come together and form an ion. It's called a polyatomic, meaning many atoms. So SO4 is 1 unit, 1 team, so SO4 needs to be in parentheses. So all of the SO4 has a minus 2. So if SO4 is minus 2 and Fe is plus 2, I only need 1 of each. 1 Fe and 1 SO4. Yes, Will?
What would it, SO with the 4 outside the parentheses be?
Doesn't exist.
But like, if it was, would be 1 S and 1 O, and then just 4 separate things of it?
Yeah, I mean, it's hard for me, that doesn't exist, so. That's like asking me what a unicorn looks like. We got pictures of it, but do we really know what it looks like? No,
I
because
mean,
we've never seen it.
It's of course a porn.
Yeah, but how do you know? We've
You can
never seen
imagine
one.
it pretty well.
We just made that up. So it would be, and from like a science chemical perspective, I can't even answer that question because it would not happen.
You know, chocolate too.
Is that
Ever.
is that
Ever.
no? It can't.
Okay.
No. I'm just pretty confident in it. 100%. No chance. All right.
Leprechauns real? That's a question.
Leprechauns are also not real. Sorry guys.
What
Neither Santa Claus. Sorry guys.
Bigfoot?
Bigfoot?
I don't know.
It's probably.
Right.
I know aliens are real.
No, Bigfoot is an alien.
All right, let's get focused here. Calcium hydroxide. Who's got it? Who have I not told? I'm trying to spread the love here today. Go ahead. You can talk about it.
CaOH and there's 2.
Ah, yes, very good. If you wrote this on your paper, you are wrong.
Yeah, put in parentheses there.
You need parentheses around the OH because this CaOH2 means 2 H's. This means 2 OHs. So the difference in bonding is calcium bonded to 2 OHs or calcium bonded to an O and 2 H's. That is very different than this. Very different. Okay, the H is actually attached to the O, and that's like a unit, and there's 2 bonds here, not 3 bonds, 2 individual H's. Some of this might be confusing, I get that. The point is, it needs to be in parentheses because OH is together. That was kind of funny. Alright. Okay. Now,
Such a subtle. Oh.
alright, good. We got some time. Right, we're done with that. Your homework's going to practice more of it. We'll go over the homework and then we're kind of done with that naming stuff. In our notes, write this down. Covalent. Now, I know we've already written notes on covalent. Let's recap. What do ionics do with their electrons? Transfer. Metals give to nonmetals. Okay. What do covalents do? Share. But there's 2 ways to share, right, Shane? Right, Tyler?
Yeah, like.
You can share.
Touch.
There you go. Ready? Ready, Tyler?
Good.
Here we go.
Yeah.
All right. Let's say you wanted to eat these. Okay.
All
right. Let's say
a marker.
Let's say I did too. All right. So we have
Okay.
4 of these delicious markers. Okay.
I want blueberry.
If I gave you want the blueberry? All right. I'll get the blackberry. All right. So now I gave him 1. I kept 3. Did I share?
Yeah.
Yeah. Okay. Did I share equally?
No.
No. I kept more. Okay. Now back to the original. All right. Now I can give him the blueberry
Yay.
and the blackberry.
Whoa.
So now I have 2 and he has 2. Did I share?
Oh.
Did I share equally?
Yes.
Okay. That was it. Alright. So, there's 2 ways to share electrons. Didn't we use pizza as an analogy the other day?
Yeah.
Alright, so, one type of covalent bond we share equally and the other we share unequally. Does anyone remember the types?
No. Bonds.
Polar?
Oh, polar and non-polar.
Okay, so polar is one type of covalent and non-polar is another type. Polar is where electrons are shared unequally. I'm going to write it a little differently though. Unequal distribution of electrons. I'm just going to put E minus. So think of the markers as electrons, and I'm distributing them equally or unequally between Tyler and myself. If I give him 1 and I keep 3, I'm not equally distributing them. But non-polar is equal. So that's when I gave him 2 and I kept 2. So we're sharing equally. So I just want you to understand, sharing equally and unequally, distributing kind of means the same thing. So this is equal distribution of electrons. So if you have a non-polar molecule or bond, the electrons are spread out very evenly. There's no poles because of that. If you have a molecule or bond and they're not spread out evenly, it's going to create like opposite ends, like a battery or the Earth. It's going to create poles. So the very simple way to explain this today is underneath here, I want you to draw one atom bonded to another, and inside it we're going to label A and B. So we have atom A bonded to atom B. We'll assign actual elements in a little bit, but first we'll just keep it as simple as possible. Alright, over here, we're going to have atom A bonded to atom A, or atom B bonded to atom B. Okay. So I also want you to think of sharing and distribution, kind of like in terms of tug of war. I wish I had that big rope, but I'm going to bring in either a tablecloth or a sheet tomorrow. And that's going to work nice. I never thought of that until this morning. I'm excited to use it.
For tug of war?
For tug of war and something else. And we could also talk about the fabric of space and time as well, if you wanted to.
Oh, what?
Black holes and wormholes.
Oh.
I'd rather not, my head will hurt.
Yeah, if you put it. Yeah.
Can't do that. Silas isn't here right now.
I'd rather not, because my head would hurt.
Yeah. All right. So no, but I'm gonna bring in something just like a bed sheet or table, something that we could use to kind of represent tug of war, and also something we're gonna learn tomorrow. Our next lab will also help with this too. But here we go. Let's stay focused. So if we have A bonded to itself, so let's say hydrogen and hydrogen, or fluorine and fluorine. All right. So they're playing tug of war with themselves. All right. Here we have 2 separate atoms. Again, hydrogen and fluorine, or hydrogen and chlorine, we have 2 different atoms. So, theoretically, if you're playing tug of war with yourself, would anyone win? Theoretically, no. Right? Because they're both going to pull with the same strength, they're both the same weight, whatever makes sense to you. All right? I just want you to go with me on the analogy that no one's going to win here. Right? Because they're pulling on themselves. Okay. Over here, someone will win, because they're 2 different people. Eventually someone wins that tug of war. Now, forget actual tug of war, forget the pizza and me sharing markers with Tyler. Now think of the actual chemistry involved. What's inside the bond here?
Electron.
How many electrons?
As E.
Think of a dot structure.
E.
If I have hydrogen bonded to a hydrogen, what would that dot structure look like?
2.
2 dots, one from one from the other. So one single covalent bond is what it's called, has 2 dots, one from each, and they share those electrons. But they share one of 2 ways. Okay, what causes the pull? Why are they fighting over those electrons? What's the word we've learned?
The force.
Electronegativity. Electronegativity is attraction for electrons. Where do we look that up?
Table N.
The last table.
Table S. All right, good. You don't have to go there right now. Stay up here, eyes up here. So it does not matter what element I'm talking about. If the same element is pulling on itself, it has the exact same electronegativity. So I'll make up a number. Let's say A has an electronegativity of 1. So if A has 1 and A has 1, they both have the same attraction for the electron. The electrons in the middle aren't going to move at all. What does that mean? No one wins, so it's shared equally. Same thing here. Let's say B is 2.5 and 2.5. If they're both pulling with the same strength, no one wins, so they're forced to share equally. Over here, it's a different story. It's 1 versus 2.5. Who's going to win? 2.5, the B atom has a higher, stronger electronegativity. Underneath this, I want you to draw an arrow pointing towards B, indicating B is winning that tug of war. And then I want you to put this vertical line kind of here. I'll explain more about what that is tomorrow. So really this arrow just explains which direction the electrons are getting pulled. Over here there's no arrow because no one wins. So under here, I'm out of room, but under here I want you to write B pulls with a greater electronegativity. Over here, again under here, I'm out of room, put a little star. No one pulls with a greater electronegativity. That's probably not the best way to word that, but basically no one wins here in the tug of war analogy because their electronegativities are equal. But over here, someone wins because their electronegativities not equal. So, after you're done writing that, let's see if it makes sense. I'll just repeat myself again because this is really important to understand. If you understand the basics, which is what I'm doing right now, tomorrow when it gets a little more complicated, it'll be easier to understand. Does it make sense to you guys that, again, let's use the chemical terms here, electronegativity, if it's the same for both, meaning the attraction for electrons, if it's equal for both atoms, then no one wins? Does that make sense? If there's an electron in the middle, like the flag and the rope in a tug of war, it's really not going to move. Everybody with me? But over here, does it make sense that B is going to start to win and that electron is going to start to come this way a little bit more? Okay. That's really all you need to know today, the difference here. That means it's unequal because it's more towards B, less towards A. This is equal because it's going to be right in the middle. Okay, underneath here, let's just get real examples. So, over here, for nonpolar, so again, just keep taking your notes here, Hankelbriefs. All the Hankelbriefs are very nonpolar because they all play tug of war with themselves. H bonded to H, O bonded to O, N bonded to N, and so on. That's as nonpolar as it gets. Over here, there's a lot of different examples. I'll just use a very simple one, hydrochloric acid. HCl is polar because Cl is much stronger than H. Now we can write that down. H is 2.2, Cl, someone look it up, I don't want to give you the wrong number. Is it? I think it's 3.2. 3.4? I'm going with 3.2. 3.2. So Cl is stronger. Over here, we don't even have to label them because, again, they're bonded to themselves, so nobody wins. That's A bonded to A. All right, this is A and B. All right, so that's a huge difference here. All right, and this is really important to remember the basics. How much time do I have? We'll stop
This
there.
is all right.
That's good enough for today.
Yeah.
Tomorrow we'll get into the more complex concepts.
Great.